Hi everyone, I'm Takahiro Haruyama. I'm working on incident response, forensic analysis, and malware analysis at Internet Institute of Japan. That is a Japanese internet service provider company. Today, I talk about anti-memory forensics focused on memory analysis. This is today's agenda. First, I explain overview of memory forensics. Second, I refer to previous researches about anti-memory forensics. Then I propose my anti-analysis method and implement plans to prevent it. Finally, I summarize my presentation. Well, let's start. What's memory forensics? Memory forensics is a method analyzing volatile data. Conventional disk forensics becomes difficult year after year because of increasing amounts of disk data or anti-disk forensic methods used by malwares. So analyzing volatile data is important to detect threats quickly. The flow of memory forensics is separated into two steps: acquisition and analysis. First, an examiner captures RAM data on victim machine and save it as a binary image file. Next, he passes the image offline on another machine using analysis tool. The offline passing makes an advantage to memory forensics. The advantage is not to use system APIs, so memory forensics can get unallocated or hidden data. For example, live response tools such as sysinternals cannot discover already terminated process or process hidden by API hooking. But memory forensics can extract the processes because it does not depend on system API and pass a binary image for itself. There are three memory image formats: raw, crash dump, and hibernation. Generally, the image used by memory forensics is raw. HB Gallery, Fast Dump Pro, Guidance WinN, and Moonsource WinDD make raw images. WinDD can also generate crash dump. If you want to examine crash dump and hibernation, you must convert them to raw because most analysis tools accept only raw image. Moonsource Windows Memory Toolkit can convert one format to another. This tool is useful when analyzing hibernation files in laptop PCs. Do you know the difference between raw image and crash dump? Okay, crash dump does not include two data areas. One is the first page reserved by BIOS, and another is address space reserved by devices. If you want to get the pages, I recommend raw image format in acquisition. Actually, can raw image acquisition tools get the first page and device reserved pages? Unfortunately, it's not true. Only WinN and WinDD can acquire them. You should add C option when using WinDD. But on 64-bit machine, do not use the option because it causes blue screen. So use C option only when acquiring 32-bit images. Okay, then I talk about analysis. I introduce two examples. I often use them. First, Volatility Framework Timeliner plugin. Volatility Framework is an open source memory analysis tool. The Timeliner plugin makes timeline on memory. It can find the date process, thread, and close socket. Moreover, it adds event logs to the timeline. For example, in this result, we can see terminated SPI bot process. SPI is a famous grammar like this, and suspicious connection opened by Explorer. After the socket was created, many threads were generated. Is that caused by code injection? We can't judge from timeline, so use another technique. Some memory analysis tools check protection flag of virtual address descriptor. That is a unit of process memory address space. The flag of injected memory space is characteristic, so tools can discover injected memory data. This is the result by red line. Red line can find injected memory pages in Explorer and display function names exported by the pages. These names like SPI init, SPI start, SPI stop indicates its SPI plugin DLL. Currently, we have some options when analyzing memory images. Mandiant redline, it's GUI frontend for memorize, HBR responder, validity framework, and encase nscript. Nscript is my work. Redline and responder supports all 32-bit and 64-bit Windows versions. Validity framework supports only 32-bit images, but it can analyze 3 format images. Encase nscript is based on validity framework. I extended my script in order to support 64-bit images. HBR responder and redline cannot extract terminated process information, closed socket, unloaded kernel drivers, and so on. I think they don't target at unallocated kernel objects. Scan modules of validity and nscript can find them. Redline and responder have a significant feature for detecting malwares, malware risk index, and data DNA. Responder also provides code graphing function for running processes. Validity framework is open source, and many developers join the community. And nscript can perform multilingual keyword search and detect similar processes by entropy in the memory image. But the total ability is slightly poorer as compared with other tools because I'm lazy. We finished review of memory forensics. The next topic is previous works about anti-memory forensics. I think there are 4 cases attacking memory forensics. Hide specific data in acquisition, about acquisition, hide specific data in analysis, and about analysis. Basically, those techniques require privilege. So I suppose kernel mode malwares can be installed on the target system. From that, I explain previous works such as Shadow Walker, Metapredator script, and anti-object carving. Then I talk about proposed method avoiding memory analysis later. Shadow Walker is proposed by Sherry Sparks and Jamie Butler. And Shadow Walker installs the malicious page fault handler to make the synchronized DTLV and ITLV. So it can prevent data access to the code. Memory allocation tools cannot access to it, but can detect the IDT entry hooked by Shadow Walker. This figure shows HBR responder could detect hooked IDT entry. Next case is a metapreter script doing anti-memory acquisition. The action is very simple. Kill specific process or prevent driver loading. Memory acquisition requires driver loading to access to raw devices. Evasion from process killing is easy because it's based on process name. In addition, preventing driver loadings has an impact on the running system. But this is proof of concept script, so the method may become more sophisticated in the future. This is an example of anti-analysis method. Some memory analysis tools use object carving. That is a technique to extract kernel object information. Generally, object carving finds the objects by searching fixed values and strings. For instance, to find process object, dispatcher header and pull header are used. But Doran gave it caution. Attackers could change the values to hide specific object. For example, pull tag and size in headers of process object are modified like this. Open source tools cannot extract the process information. So he proposed robust signatures causing blue screen or functionality failures if the values are changed. On the other hand, closed source tools like Mandiant Memorize and HBGR Responder can find the hidden process. How do they find it? Moreover, object carving is one of the operations executed in memory analysis. Then, are the other operations robust? That's why I started to research the internals of memory analysis tools. From now, I explain my anti-memory analysis method. I've researched 3 major tools such as Volatility Framework, Mandiant Memorize, and HBGR Responder Community Edition, and found 3 operations executed in memory analysis include a few unconsidered assumptions. Proposed method modifies 1 byte of data related to the operations. The data is defined as abort factor. Abort factor means the data modification about analysis by 3 tools, and the modification is uninfluential to the running system. After the modification, I can install and use applications, services, and kernel drivers. The evaluation time is a few days to 2 weeks, so I don't know the impact in long term, like 1 year. The mentioned 3 operations are batch address translation in kernel space, guessing OS version and architecture, and getting kernel objects. First, I talk about batch address translation. Before showing implementations of tools, I summarize batch address translation in Windows. This figure shows inter-32-bit batch address translation. The batch address is separated into 3 indexes, and they indicate physical address offset in each memory table. For address translation, OS needs the start address of page directory entry. That is called directory table base, DTB. Each process has different DTB values for memory protection. When the process context is switched, OS loads DTB of the active process into control register. Then address translation for the process works. Initially, analysis tools must get the DTB value for kernel space because crucial metadata such as process, driver, connection objects are stored in kernel space. DTV is stored in each process object called eProcess. So through the scan, eProcess signature of kernel processes and get the DTV value. As long as I researched, there are two process objects including kernel DTV: system process and idle process. Object carving is generally used to find all process objects in a memory image. Process object with kernel DTV, also no exception. This figure shows process object structure and its headers. Pool header includes pool tag. If the object type is process, the pool tag is pro. Object header has flags that is fixed value. And dispatcher header and DTV are included in K process that is located at the head of eProcess. eProcess has image file name. This is the process name. Some of analysis tools try to find kernel DTV value using these fixed values and strings. Volatility framework implementation first searches dispatcher header to get eProcess. In volatility, first 4 bytes in dispatcher header are used for search. Then check whether the image file name is idle. If so, get the DTV value in K process. Mandiant memorize searches system to find image file name in E process and validates by using dispatcher header in the K process. Dispatcher header values change according to OS version, so the header values of all versions are checked. Besides, memorize validates the eProcess using flags in object header and pool tag in pool header. Specifically, memorize calculates distance between pool tag and eProcess based on the flags value. The distance depends on OS version. Then search pool tag from eProcess position and check whether the search hit offset is equal to the calculated distance. If that is correct, get the DTV values. HPGRE responder searches dispatcher headers to get the eProcess. Before the search, responder registers dispatcher headers of all OS versions. Then get the DTV from the result and validate it at virtual memory discover function. Responder seems to be equipped with the algorithm guessing kernel DTV. If kernel DTVs are not found, guessed DTV value is used. I don't figure out the algorithm perfectly, but I found the routine using value 0 as kernel DTV parameters and trying to initialize virtual address translation in kernel space. I sum up data related to virtual address translation in kernel space. X in abort factor column indicates the data can be modified without blue screen or system errors, and the modification aborts the memory analysis. Volatility framework tries to find idle process, and both of data are abort factors. Mandiant memorize definitely check whether the eProcess is system, but all values are abort factors. HBGI responder scans dispatcher header and uses the extracted DTV values. But if the scan fails, it guesses DTV value using original algorithm. The algorithm doesn't seem to use fixed values and strings, so it's safe. The second operation is guessing OS version and architecture. Size and definition of kernel data structures differ according to OS version and architecture. For example, process object size is like this. So analysis tools need OS version and architecture information of the target image. All analysis tools, more or less, refer to debug structures for guessing the information. This figure shows several debug structures and their relations. Kernel processor control region, KPCR, includes KD version block that points to DBGKD get version 6.4. And debugger data trace is a pointer to KD debugger data 6.4. KPRCB has rich debug data, including current running thread, and located in KPCR. DBGKD debug data head 6.4 is often used as carving signatures and the header of KD debugger data 6.4. Kernel base is a base address of Windows kernel. This member is service pack version. PS active process head and PS loaded module list are used for accessing to process and kernel module list. I will explain them later. Volatility framework requires profile option specifying OS and architecture. If the version is unknown, we can use image info plugin. This plugin guesses OS version. Specifically, the plugins can owner tag and size in DBGKD debug data header 6.4. The tag is fixed string KDBG. On the other hand, the size is changed by OS version. That's why this value is used by the plugin. Memorize supposedly determines OS and architecture based on dispatcher headers. Then validates them by using an offset value of image file name in eProcess. There are image file name offset values for various OS versions. Memorize uses them. If the OS measure version is decided, Memorize checks the version is correct by executing address translation of thread list head in kprocess. Then get service pack version from NTCSD version in KD debugger data 6.4. Responder first gets kernel-based address from debug structure and validate the P header signatures, those header MZ, and LT header P. Then get and check OS version from operating system versions in optional header. Finally, get more specific version like service pack. Responder compares time data sum value in file header. Okay, this table shows data summary related to the second operation. Modifying owner tag in DBGKD debug data head 6.4 seems to have no impact on running system. Dispatcher header and image file name of system eProcess are abort factors, as I explained earlier. Thread list head is address value, so the modification is not possible. CMNT CSD version can be modified, but the modification cannot avoid most memory analysis because key data structures remain unchanged even if the service pack version is updated. The only exception is Windows 2003. This version changes structures according to service pack version. About responder, we can't change kernel-based value because it causes blue screen. P header signatures can be modified and it can avoid memory analysis. But after the modification, we can't start new services and load kernel drivers. So that cannot be a avoid factor. Operating system version in optional header is a avoid factor. Time data stamp is not, because the data affects only service pack version. Third, getting kernel objects. There are two methods to get kernel objects. One is traversing linked list or binary trees. Generally, this method accesses to kernel objects using special read or root addresses such as PS active process head for process list, PS loaded module list for kernel module list, and VAD root for batch address descriptor tree. The other is object carving. As I mentioned earlier, the easiest way is to use fixed values like pool header or dispatcher header and so on. I looked into the implementations of three tools. Researching all of kernel objects is not realistic, so I focused on process object, eProcess. Before explaining individual implementations, I want to fill in the gap about process linked list. Process list is made by two-way link. Each process includes active process links, that is list entry type, and information of forward link and backward link. All links to data are eProcess objects with one exception. The exception is PS active process head. This includes only link information. It's not process object. PS active process head and system process are bound up together. The f-link of PS active process head points to system process and vice versa. Volatility framework traverses process linked list by searching DB-GKD debug data head 64 and get PS active process head in KD debugger data 64. Remember debug structures as I explained earlier. Volatility framework also does object carving. It uses pool tag. On the other hand, Memorize also does object carving, but it does not depend on fixed values and strings. It finds eProcess based on address values. Specifically, Memorize reads data from memory image by 4 kilobytes and validate whether values included in the data are correct as address pointer values of eProcess. For instance, is DTB 32 bytes aligned? Is the top of 4 digit of PV7 FFD? Is the top single digit of active process links 8? Memorize also checks other address values for validation. This method is very similar to robust signatures proposed by Doran-Gavit. HBGR responder accesses to process objects by traversing linked list. But responder does not use PS active process head. Instead, it extracts the initial eProcess from current thread in KPRCB. During the access to process list, responder checks whether image file name of eProcess is system several times because it must avoid to get data with PS active process head as eProcess. In this sphere, for example, the routine tries to get eProcess next to the current one. If the current eProcess is system, the routine gets data pointed to by forward link. If not, get backward data. System strings is several times compared like this in responder. I wrap up the third operation with this table. DB debug data head 64, we can modify it. PS active process head is a point value, but its modification seems to have no effect on running system. I think the reason is KT debug data 64 is used only for debugging the system, but I'm not sure. Long-term evaluation may change the result. Pull tag is used for object carving, but the alternation never causes analysis about. We can't modify address values because the values are essential for process management. Current thread is not allowed to change because the modification causes blue screen. eProcess pointer in case thread also cannot be modified. Okay, this table shows abort factors in 3 operations. 5 factors in volatility, 6 factors in memorize, and 2 factors in responder. Generally, checking as many data as possible is recommended, but if the data are easy to modify, the validation works negatively. And analysis tools lose their robustness. I performed all data modifications using Windows Debugger, WinDBG, but I also wrote POC driver, modifying 1 byte per 1 analysis tool. Now I show you a demonstration using the driver. First, load a kernel driver into XP virtual machine. The driver modifies 1 byte of the following data: size in dispatcher header of idle process for volatility, pull tag in pull header of system process for memorize, measure operating system version in P header of Windows kernel for responder. Next, check the modification using debugger, then acquire the memory image using Live Cloud KD. Finally, analyze it using 3 tools. Before the demonstration, I show normal results to display process list for memory forensic beginners. This is the result of volatility framework PS list command and memorize result and responder. All 3 tools could display running processes in the image. Then how about the demo memory image with malicious data modification? Let's check it. This is a debugger view, and this address is idle address, and this address is system address. So this is a size in dispatcher header of idle process, and this is the pull tag in pull header of system process. This is the kernel base address, and this is a P header of Windows kernel. The major operating system version offset value is here. The value is 118. So this is kernel base address, and this is major operating system version offset. So this is the major operating system version value. Okay? Let's load kernel driver. Done. So make sure the values are changed using debugger. Skip a few seconds. Sorry. The size is changed to 0. The first byte of pull tag is changed to 0. And the major operating system version is changed to 0. So it's time to acquire memory image. I use the Live Cloud KD made by Mash Switch. I like it. Skip a few seconds. Done. Sorry, never mind Japanese. Demo bin was generated. Finally, analyze it using 3 tools. First, volatility framework. Executing ps-list command. Volatility fails to find the kernel DTP of idle process. This is the error message. We can't find out the cause. Next, memorize. Skip a few seconds. select demo bin, and analyze it. We can't see the error message. But memorize fails to find kernel DTB of system process. This is the error message. Maybe OS identification or some kind of errors. Finally, responder. And so I forget one thing. The result in memorize is empty. Nothing found. Ordinarily, the processes are shown. And lastly, responder. Select demo bin. Analyze. It takes some time, so skip it. Responder fails to identify OS version. And the error message is here. Virtual memory discovery failed. That's it. As I explained until now, all analysis tools have room for improvement to prevent errors. So I propose a few improvement plans. There are 3 plans: guessing based on address values, minimum guessing, and separating implementations to get kernel objects. First, guessing based on address values. The modification of address values often causes blue screen or function failures. For example, KPCR object carving technique uses self-PCR and PRCV members in KPCR. Self-PCR points to KPCR address, and PRCV points to KPRCV address. So analysis tool can discover KPCR by scanning virtual memory space. If the members are modified, the system crashes, so they cannot be modified. Don't use fixed values and strings as much as you can. The second is minimum guessing. In other words, don't guess as much as possible. For instance, support crash dump format. Since crash dump includes debug information in the first page, several values can be extracted, such as DTV, OS version, PS active process head, and so on. However, please trust only values extracted from CPU registers. In WinDD implementations, DTV value is copied from CR3 register, like this. So you can use it without malicious modification risk. Other values like OS version and PS active process head can be modified. Volatility framework already supports crash dump format. The second example of minimum guessing is to support argument passing options about DTV and OS version. Volatility framework also supports it. Volatility users can specify OS version by using profile option and DTV value by using DTV option. The third is separating implementations to get kernel objects. Memorize requires getting DTV value in kernel space or about the analysis. On the other hand, volatility also needs a kernel DTV value, but all commands don't use it. For instance, volatility has two commands to display process list, PS list and PS scan. PS list fails if kernel DTV values are not found, but PS scan command can display process list without it because the implementation is object carving only. It does not translate batch address. So I think it's better to display result minimally extracted by object carving than analysis support. I wrap up my presentation. Proposed anti-analysis method can avoid memory analysis tools by modifying only 1 byte. I did not test all OS versions. I tested Windows XP and 7, 32-bit and 64-bit, but all abort factors don't depend on OS-specific data structures, so the method is effective for memory images of all OS versions and architectures. About the impact on the running system, I think long-term evaluations may be needed. Finally, I hope developers improve the operations based on my suggestions or other methods, and users figure out internals of memory analysis and deal with analysis errors properly. That's all for today. Thanks for coming. And please fill in the speaker feedback surveys. Thank you.